Um, so let's get started. Welcome everyone. This talk is going to be about tuning Kafka pipelines. Like I said just a moment earlier, I'm Sumant. I work in LinkedIn about a year and a half now in Streams infrastructure. My most of the day-to-day job is about making sure Kafka works fine, and it's not just Kafka but everything around it. I've been a contributor in Apache Kafka, did a few things in open source Kafka, working on a kit right now. Um, in my previous life, I used to do a lot of C++, not as much anymore. So I wrote a blog on C++, I wrote a wiki book earlier. I did several Silicon Valley Code Camp presentations on that. Through that I got an award from Microsoft Most Valuable Professional, so that's good. So let me just jump right into it. Today's topic is not about C++, it's all Kafka. So here is how a truly global Kafka pipeline may look like. So we have these dotted lines are pretty hard to see, but this is actually meant to be East Coast data center, and data is being copied from one Kafka cluster to the another in just the East Coast data center, and also to Gulf Coast. By that I mean the Texas area, and also to West Coast. This is the same source of data, and to Asia. So here is how a Kafka pipeline that is truly global might look like. But that's just, we will come back to this a little later. So first of all, we'll go through some basics. So Kafka is a distributed messaging system that's rethought as a distributed commit log. In a Kafka system, you have, of course, producers, the Kafka cluster in the middle, multiple brokers, depending upon how much traffic you have to sustain, and consumers. Producers produce data, and Kafka stores this data in the logs, and logs are essentially just files. It's an append-only log. In a given application, generally there is a few topics. Let's say just one topic that application is interested in. So producers will publish to that topic, let's say topic T, and consumers will consume that topic. That topic is generally divided into multiple partitions, and this is purely for parallelization or handling the throughput of a particular topic, because some topics are pretty low in bandwidth requirements or traffic, and others are really high. So if you have a really busy topic, you would have a lot more partitions. In this diagram, there are only two partitions for this topic, just for simplicity, P0 and P1. The P0 partition is the leader for the P0 partition is broker 1. What that means is all the producers that want to write data to this partition will go to broker 1, and those that write data to the other partition will go to broker 2. Why is it done this way? Because the partitions are divided among brokers, and they are replicated. In this particular case, the P0 prime, I hope it's readable over there. The P0, the leader broker, the data from that is replicated into the second broker. This is the follower for this particular partition. But the relationship can be the other way around for, let's say, P1. As you might guess, partition P1, broker 2 is the leader, but broker 1 is the follower in that case, and it gets data from it. So essentially, each topic, all partitions in the topic get replicated within a Kafka cluster, and that's how it achieves higher reliability, availability, and durability of data. On the consumer side, let's consider a simple consumer here, which is just a single consumer tool. Of course, it has to consume data from both partitions. So that's that. In this case, there are two members in the group. They are part of the same group, they share this group ID, and they kind of distribute the work between themselves. They share the workload. So one of them just gets data from partition 0, the other one gets data from partition P1. If there are more partitions, they would distribute them trying to be even. So that's the I guess, how Kafka producers and consumers work.
Is it not efficient for A2 to get P1 prime?
Again, is it not efficient to get
Data for A2 from P1 prime instead of going to the broker to?
It is actually possible that as long as the follower partition, the follower replica is actually in sync with the leader, then yeah, in theory you could actually read data from the follower as well. But that's not how it's done today. There have been some discussions that this could be done to spread the read across multiple brokers, but you could do that by adding partitions as well, because as you have more partitions, they get distributed around brokers, and you can have even working.
So the replication is just to ensure resiliency of the communication, right? In case the broker 2 fails, or the broker
That's
1.
right.
Okay.
So in case of a failure, one of the brokers fails, then as long as the partition, the follower partition is actually up to date, the consumer can simply fail over to that, and it kind of happens.
Is it a one-to-one failover or one-to-many?
What do you mean?
Do you have for each broker another one, which is going to ensure the resiliency, or for you might have multiple?
I'm not exactly sure. So but let me see if this answers your question.
Yeah.
So there are of course many partitions a single broker is probably handling.
Yeah.
In this case, there are only 2, but there could be P0, P1, P2, and many more.
Yeah.
If the broker fails, then all those it's no longer a leader for all those partitions.
Yes.
So someone else, broker 2 or many more down below, could pick up the slack. So as far as partitions are concerned, yes, one broker's partitions could fail over to many other brokers.
And that's because P0 and P1 prime, or P0 prime and P1 can be distributed over multiple brokers, right?
Yes, that's exactly pointed. Yeah, P0 is actually replicated onto another broker.
Yeah.
Just one.
But let's say you have, I'm sorry, I don't want to interrupt you. Oh, but let's say you have P0, P1, P2, P3, you could have P1 into broker 2, P2 into broker 3, and P3.
Yes.
Okay.
Yes. Yeah, the partitions get distributed
That's what I was
in a kind of
what
balanced
you mean,
way. Yeah, I think it's called the preferred leader election in Kafka, and that's how they do that at the time of topic creation. So this is just to give an idea, like moving data is pretty important in digital enterprises. I'll kind of speed it up over here because applications, if you connect applications one-to-one, you end up creating n-square connections between them. But instead, if you have any messaging technology like Kafka or others, you create ON connections. So that's just the benefit of the architecture, right? Hub and spoke architecture. But why Kafka specifically? So this is how a Kafka pipeline typically looks like. Kafka-based pipelines, the key value add is that it gives you a very large, reliable buffer between producers and consumers. So your producers can be, let's say, continuous producer, or maybe a hourly job, or maybe a daily job and whatnot. And you can mix that with consumers on the other side, which can also be daily jobs or continuous or hourly jobs. The performance can be very different as well, because of the Kafka cluster in the middle, the producers and consumers are not directly coupled. So they can come in and go at any time. They don't have to be up at the same time. So they can be at different times. Performance is decoupled, so consumer can be slow. That's okay, as long as all the data is stored in the Kafka broker. Yes, you can continue. So that's the main benefit you get by using Kafka. And there are several others, but these are kind of the main ones I think. For availability of this data, once your producer has produced some data, some tracking data or not, you probably also want to make sure that this survives even data center failures or for whatever reason you're not able to consume data from your first cluster. You have to replicate that data over to a different cluster. Perhaps your different data center, perhaps your different continent, because who knows, you want to have the availability of data everywhere. So in that case, Kafka pipelines come into play. But this is a typical structure. Of course, there is a source Kafka cluster, and the purple box is a mirror maker, which makes the only job it does is just copies data from the source Kafka cluster to destination. And the consumers could be again, different data center or even the same one. We'll look at a much, complicated example later on. Question?
Quick question is, just to get started with a very simple system, how many of those components I should be having? Can I start with just one component?
Not really. I think the smallest pipeline, if you will, or even smallest Kafka system would have three things. Well, here is actually mirror maker, so let's not talk about that slide. But at the minimum, let's go back to earlier slide maybe. Yeah, the smallest would be a single producer, a single broker, a cluster of one broker only, and a single consumer. So you have at least three elements.
My confusion is, if I have a message producer already,
Yeah.
and why should I have another Kafka producer in pretty much Kafka source? Because I could use one Kafka component pretty much as a bridge between my message producer and the message consumer, right?
Okay.
Can I not do that? Instead of having
If you already have a producer, does it speak Kafka? Or
let's assume that it can be connected with Kafka.
okay.
But I would like to just have one component of Kafka instead of many, because every time I add a component, I believe there is significant overhead. I need the infrastructure, I need maybe storage and
Yes,
kind of cost
running
justification.
Kafka is not a trivial thing, because what I've not shown here is a zookeeper cluster. That's hiding behind this big square. So yeah, you have to manage zookeeper and brokers.
Okay, I guess the follow-up question would be, when is the right time to actually introduce Kafka if I have the opportunity to architect a new application?
Okay,
When-
right now.
when is the-
Right now is the right answer. Maybe yesterday was the right answer. It's just it's important to have Kafka in place in such a way that it should be multi-tenant. You cannot have a Kafka cluster for a specific applications requirement. It should be multi-tenant so that multiple applications can be run through that pipeline. So okay, in the interest of time, I'm gonna skip this slide as well, or maybe not, because some of these details will become relevant later. All I want to say here is mirror maker. Here is a single process of mirror maker. It has more consumers than producers. That's something will become relevant. This consumer is consuming data from source cluster, and a single producer publishes data to the destination Kafka cluster. And that's just single process. So you could have many more processes in a mirror maker cluster, which will become relevant later. So there are many aspects of Kafka pipeline. There could be, if we were to talk about all of them, then whole day is probably not going to be sufficient. So I'm going to skip most of them. I'm going to post these slides on SlideShare. You could go through what I want to say about each one, just a little bit, one slide each really. We'll dive into some of them in detail. So of course, reliability and availability is important, because data must be available. The applications need to continue working even in case of failures, even say disaster recovery scenarios as well. And so that goes without saying. And Kafka achieves that by means of replicating between brokers, and Kafka pipelines achieve that by copying the whole data over to a complete different data center. Alright, so it's a different failure model. A single broker failure is different from whole data center. So there are some replication topologies you may be interested in. So here is a hub and spoke architecture where you may have multiple sites that produce data individually, and that data is sent over to a central site, and that's where aggregation and overall results for an enterprise are computed. This one is a crossbar architecture. This is how we run it in LinkedIn. You have they are all active. They are all running at the same moment. The production clusters, they are receiving data from different parts of the world, different East Coast or West Coast, and then all of that data is replicated into these kind of lower level or second level Kafka clusters. All these arrows here are actually mirror maker pipelines. So for any reason, we had to do traffic shifts, like going from for some reason apps in this are not well behaving, completely unrelated to Kafka, and traffic had to be moved to a different data center. We can do that because this is actually active setup. Of course, you have to have spare capacity to take, let's say, 33% of the load over to two others. So now the whole site is run over, let's say, not two clusters, but essentially two data centers. Let's talk about durability real quick. So durability also interacts with throughput and latency. The producer configuration becomes, you control durability by producer configuration. If you do not want any durability at all, you would say x equal to 0. That means I don't care, here is the data, and whether broker receives it or not, if for some reason broker decides to reject it, you still do not know. So you can go as fast as you can, but you might lose data. X equal to 1 is saying, well, I want an acknowledgement from at least one broker, so that, okay, one broker has it, I can move on. But I don't know if it has been successfully replicated to others. So that means you're saying, okay, if that broker goes down, the only guy who had data, then yes, your data is probably, you lost it. So there is another level which is x equal to all. This has lowest throughput because the data is replicated, like in the earlier diagram, from the leader broker. You send it to one broker always, and it decides to, it's spread over, is replicated from that broker to other followers. And when all followers, well, not all followers, depending upon your replication factor, let's say two other brokers get that data, then you can move on. So that you cannot wait for that replication to happen. And it has got, of course, throughput and latency consequences when you configure the producer levels. Okay, so now we are getting into throughput. Now, like I said earlier, the producer and consumer throughput can be very, very different. Kafka can handle that. If you want to increase throughput of your entire pipeline, or let's say particular Kafka cluster, then you would just add Kafka brokers. That's the simplest way to do that. If you have hardware capacity, if you can run more brokers, that would be the direct way to increase throughput of your entire Kafka cluster. If you have a single application and you want to increase capacity or increase throughput for that, you might consider adding more partitions, because for the topic it's interesting. So application uses a topic has partitions, maybe 10, 15, whatever. You double those partitions, so now you have a lot more resources allocated throughout the cluster to handle that. So you increase parallelization by adding that. But how about the performance of the pipeline itself? So this is actually, on the left you have one data center and another data center pretty long, is long distance away. Here, this Kafka mirror maker, the producer on this side is sending data over long distance internet link. And the consumers, of course, over here are talking to source Kafka cluster, which is right there in the same data center. So latency over here is pretty high and not so high over here. An alternative topology would be move your Kafka mirror maker onto the other side so that your producer has very low latency, but the consumers have to go over the internet link. And it turns out this is perhaps this is the recommended style of running Kafka mirror makers, because as I said earlier, there are many more consumers in Mirror Maker. They can batch data much more. We'll come back to that in a few slides. And they can go, even if they are going over long distance, you can maintain higher throughput. So the configurations. So let's look at these in a little more detail. I'm going to slow down a little bit over here. I just want to check how am I doing on time. All right, not bad. Right, exactly on time. So let's look at producer configurations. We'll look at all of them, and these are not exhaustive, by the way. These are just those that I'm most familiar with and perhaps come up most often. So the goal here is to improve performance of each component. So let's start with producer on the other side. Batch size. So batching, as you might know, is perhaps the most important optimization you can do to improve throughput. You want to send as much data as possible in a single request. So when your producer, when your application is sending a message, a single message, Kafka is going to, well, let's say you call send multiple times, so you have multiple messages. Kafka is going to put them together in a single batch. And it's not going to send it right away. It's going to hold on to it for a second or two. I'll come back to that. And it will put together all these batches that are going to the same broker in a much larger request. So there is at least 2 levels of batching that's going on when you're dealing with producer. So going back to how long is it really going to wait for before sending your message right away? It's linear. That's what it is. So it's a way of saying, well, when you send a message, don't really send it right away. Wait a little bit, because I might have another message right after, and if I fall within that window of linger, then those 2 messages get put together in a single batch and get sent over to the broker. So you can configure the linger timeout as much as you want, and chances are batching will improve with that. Of course, you can control batching with size as well. Like, okay, don't wait for too long. Just as soon as the batch fills up to particular bytes, just send it. And that's it. So those are the 2 very important tunables you have. Compression type tends to be important in pipelines. Some compression algorithms are pretty efficient, CPU efficient, but don't achieve that much compression, and vice versa. They take time, but really get you compression. So that's something you can choose. Acts, we talked about acts in terms of durability. Most of the times that's not a configurable, in a sense. An app requires certain level of durability, and that's not an option. You cannot really, hey, for just performance, let me change acts today. No, you cannot really do that, because you're basically changing your durability requirements. So usually that's not an option. And then there are many others, like configuring the internal buffers for the producer, the operating system level buffers for TCP. So it's just on and on and on. So you can dig into those. Maybe I should have. Yeah, I have a link to the configurations in Kafka, so you can take a look at this. Let's go on the other side, consumers. So for an application, like I said, if you want higher throughput, just add more partitions. That's the first thing that comes to your mind, because it's usually pretty easy to do, and it really does make a difference, because now you have many more partitions and resources are devoted in the broker, in Mirror Maker, and everywhere that help improve your performance. You get more parallelization. You have more for each partition. You have pending requests, right? So if you double your partitions, you have twice as many pending requests for sending data. So things just speed up very nicely. But then, of course, there is a limit on how many partitions you can really increase. You cannot just keep on adding them. Another tunable you have in case of consumers is the same kind of batching optimization done from the broker side while sending data from the broker to the consumer. So you can configure how much data I want to receive in a single response, in a single batch of a response. You can configure that with fetch, message, max pipes, and that will send you larger and larger messages if you so want. let's look at, this is making sense so far. So let's look at Kafka broker configurations. The most important, I think, factor that determines the broker's performance is how much replication it's doing and how. The replication is, as I said, it's for durability between brokers. Each partition, each leader is sending data to the followers for availability of data and durability. You can control the number of threads that each follower is using to get data from the leader. So it has again similar effects as adding parallelization. And similar batching optimization is also there between brokers. So as you can see, the batching optimization is pretty much everywhere in Kafka because it's for performance. This will become somewhat relevant later on. The brokers replicate data either over plain text or over SSL. And SSL unfortunately has some overhead. And it is so much so that we had to kind of disable it in an example I will talk about to get more performance for replicating data just within a single cluster. Most of the times when you're going over the internet, you have to have SSL enabled, so you don't have any options. But a single cluster lives in a data center, you may want to turn it off, or at least for time being, while you expand the cluster, just to get to the data. In Mirror Maker, of course, the producers and it's just a combination of producer and consumer. So all the configurations we talked about, producers and consumer, are relevant for the Mirror Maker.
Question.
Sure.
Does the number of partitions impact the producer throughput?
Number of partitions, whether they affect producers?
Producer throughput, yeah.
Producer throughput.
When you say that's all,
I cannot imagine why it would affect, because even if it's x equal to all, it's not about saying to all partitions. It's saying make sure that if I have a single partition is replicated twice, so there are 3 copies, then it's saying, okay, make sure it is in the disk of 3 brokers, and then acknowledge. That's what it is. So you could have 100 partitions, all of them replicated 3 times. So no, I don't think the partitions immediately affect producer performance.
it may affect because if the producer need to, in Kafka you kind of have some rotor or producer want to because the rotor will control which partition you will write to.
Yeah,
So
yeah.
if you have more partition, for example, although you have 1 partition,
You have more
you
batching
only
opportunity.
send to that one. But if you have 1,000 partition, that rotor that
I think
everyone
that's a good point.
decided, so that may
Right, I think this is going back to the batching optimization, right?
Yeah.
Because now you have 1,000 lanes, parallel lanes to send data over. Yeah, a request could pack in many more batches for many more partitions at the same time. Yeah, I think that makes sense.
You know,
But it groups the partitions for a specific broker, right? It's not about send partition by partition. So all the
It's not,
partitions
well,
belonging to the broker and then batches them.
right, but there is one more level of batching, which is a broker, let's say, has 5 partitions, and a producer has data for that broker for all 5 partitions. The request that is being sent out will contain batches for all 5.
Exactly.
So now, tomorrow you increase the number of partitions, it has 50 partitions in a single broker. It will make much larger requests, perhaps with 50, all 50 partitions, send a much bigger one. So yeah, I think it's possible to improve, throughput with that.
I have another simple question. So, how many partitions should we use in our kind of batching? So, what's the recommendation?
Yeah.
Because the
Good question.
more it will increase the parallelism, but it will have some other overhead. For example, it will impact your routing. It will have more replication.
Mm-hmm.
So, it will use more open files.
Yeah, that's right, absolutely. So I don't have an answer off the top of my head. I know that we have a formula that we kind of, our customers who are at the edge of like, okay, can I have like 500 partitions? And it's like, well, why? because we have this much QPS, this much each message is very large, and blah blah blah. Then we go and look at based on essentially the answer depends on what's your QPS, the size of the message, and how well does it compress. That also becomes a factor. Yeah, based on that we determine how many partitions are missed.
What's QPS?
I guess queries per second, but that's not the right word. Essentially, messages per second. All right, moving on. So some of this, actually much of this will be relevant in the example later. I'm gonna skip. We'll go through latency really quickly. Latency is again, latency and throughput kind of go hand in hand. They interact with each other. Latency tends to be in a few hundred milliseconds, generally from in a Kafka pipeline, from including the maker. But that SLA can be fragile because if the mirror maker rebalance, then it may take, especially if it's a large cluster, it could take a few minutes. Then you have to really make sure that your latency SLA is not like a second or 2 or 5 seconds. It's pretty hard to enforce that in a Kafka system. 5-second latency. Well, because you have to consider other situations like maintenance and rebalances. Those are cases where it doesn't happen, but most of the times data gets through pretty fast, under a second. But it cannot be your SLA because in some cases it doesn't. So I'll leave it at that. There are of course configurations for tuning that. Linger of course affects it because linger is an explicitly adding latency. So there are actually many more aspects of Kafka pipelines. You can look at these slides later on. I will post them on SlideShare. Transformation, there is how do you make sure load is fairly distributed, how do you do migrations and upgrades, topic lifecycle management, how do you create topics, where do you create them when you run a pipeline. So you start from the source cluster or destination, it becomes pretty important. DDoS prevention, because you want to give, you don't want to just fail over when some application doesn't work as per expectations. So I skipped past those pretty fast. That was actually planned because it's about only 45 minutes. So the next 12-15 minutes or so, I'm going to talk about a real life, Kafka tuning, performance tuning experiment. And yeah.
Have you talked about Zookeeper? Tuning Zookeeper for Kafka?
Good question. And not in this talk. I have not run across situations where we had to tune Zookeeper.
Okay.
Although I would say this, creating, well, depending upon how you're using it, you don't want high write throughput in, you are not going to get it in Zookeeper. So make sure anything that's asked for too much writes from Zookeeper, that's just not going to fly. Okay, so going back to the pipeline on the East Coast, and data from East Coast, of course, this is replicated on the same data center. This is second pipeline that copies data over to the Gulf Coast. Third one copies data over to West Coast data center, and the last one to Asia. The problem that we saw was replication performance. The mirror maker replication performance over to West Coast and Asia was particularly bad. The others were pretty good, but not over here. So we had to do something about it. And the overall SLA for the customer here was that they used to push data from the source. It was essentially a Hadoop cluster. Number of really large number of mappers used to push data, and the push used to finish in about 12 to 15 minutes. They wanted data over to the other side under 30 minutes. So we'll see what we saw was replication to Gulf Coast and East Coast was going relatively fine, 22 minutes, 38 minutes. So it was working just fine. But replication to West Coast, this is again going from East Coast to West Coast, took about 54 minutes. And yeah, by the way, we were talking about, we had about 100 gigabyte of data that we had to replicate in a single topic. So 54 minutes here and almost 3 hours for replication over to our Asian data center. And one curious thing you might notice, there was a really long tail for replication in over there. So that was particularly bad. Like, why is there is such a long tail? So we started investigating. First thing we realized was that CPU utilization on mirror makers was particularly bizarre going to Asia. So now, mirror maker, one might think it's actually a IO bound process because it's reading data on one side, sends it on other side, but it's actually not, because it has to decompress data, and because of that it ends up being a CPU bound thing. So the CPU performance, the CPU utilization of the slowest mirror maker was bizarre like that, and it is essentially on average it was about 16% or so, while the best performing mirror maker was nicely pegged at about 100%, like pretty very stable. It's absolutely not stable here. The next slower was also kind of erratic, kind of somewhere in the 40% range. So that was the first kind of hey, why is mirror maker not doing its thing?
Are they handling different messages or different types of messages, or are they all handling the same?
They are handling exactly the same message. They are all these mirror makers. They are reading from the same cluster, same source cluster, same data.
And the CPU is also the same.
Yeah, CPUs, the machines were also the same, right? And based on some empirical, some historical evidence, we knew that a good mirror maker kind of looks like this. It's pretty smooth, during the push, the CPU utilization is like really pretty much pegged at 90 or above, and kind of nicely goes down once it's done all the data. The different lines you see are because of different processes. They finish at different times a little bit because not all partitions have the exact same amount of data. So some of them finish a few minutes earlier, some of them finish a little later. Question?
What's happening on either side of the plateau? So you have it's going up, plateauing, and then going down again. What's happening when it's going up and going down?
Right. So in case of Venice, you can read about Venice on LinkedIn blog. The way it works is their customer start so-called Venice push, and it's essentially a map reduce job that used to run about 12-15 minutes, and that's what you see here. So before that, there is nothing running, and this was actually much earlier than this was kind of, they were bringing up the whole Venice system, so they didn't have other customers other than some select few. So they were testing performance and all. So they started a push, and therefore the pipeline kind of comes to life, and then mirror makers get busy. That's why you see ramp here, and as soon as they are done, they're done. Okay. So just quick background on what the setup was. On the producer side, we have 100 gigabytes of data. And in the brokers, we had about this broker, the source cluster, just four brokers, 32 cores each, and 256 gigabyte of RAM. The brokers were replicating data over SSL to become relevant, and replication factor for this topic was 3, and AX equal to R. That means, okay, please replicate this. I want maximum to replicate. We had about 200 partitions. And this is, by the way, where the problem was there, right? And this is not a solution, just set up. And mirror makers, we had each, the purple box here, about 80 or so consumers in data. Each one had 80, so it's like really, fan out is really high. And 8 producers sending data over. These two were long distance.
A question.
Sure.
Where's the decompression happening on the purple box or the
Yes, a purple box. The decompression happens here. So it's essentially just checking correctness of data. It doesn't it doesn't decompress it. It receives data that is compressed, decompresses it,
To do
make sure
series-
it
to do
checks
series.
and everything is right.
Yeah.
When it's right, then it takes the compressed data and sends it out.
So what goes on the load pipe is compressed data.
Yeah, if going out from mirror makers is compressed.
I have a question. So in this diagram, are the mirror makers all on the source cluster or what?
Excellent point. I'm going to come back to that. Not in this, I mean, there is one mirror maker that's on the destination side, right? So this one is doing remote consume, which is the recommended style. I'll get back to your question in a second. So one of the main reasons, of course, of high latency, the reason was latency because of the low throughput. So we saw that, okay, it's pretty high, almost quarter of a second round trip latency from East Coast to Asia, and pretty high even to the West Coast. So clearly that was contributing to low throughput of mirror makers and low CPU as well. A textbook solution would have been to move those mirror makers onto the other side, right? Because hey, these producers now just go a small hop in the same data center, and the consumers can go over long distance internet links and can fetch data much faster. But this is how one would have done it if we had time. But we couldn't do this at that moment because first of all, you have to have capacity in your destination data center to start a new mirror maker cluster. You have to open up firewall rules because now you have incoming connections for consumption rather than a producer, which is outgoing connection. So because of those reasons, at that moment we could not move the clusters over to the other side. But that would have been a really good strategy to actually fix the performance problem. So we saw a few other problems as well in the cluster. When Venus used to push this data in the source data cluster, there were very high number of under-replicated partitions. Now I have not quite covered what that means, but it's essentially Kafka's way of saying, hey, I'm not able to keep up with this incoming load. I cannot I cannot replicate this fast enough. There were a whole bunch of them. They were just pushing data way too fast. So the solution ended up being replacing them with reducers. Instead of like 800 producers, significantly less reducers were used for pushing data. We also turned off interprotocol SSL so that replication performance goes up. That sort of covered, sort of handled under-replicated partitions pretty well. So, but that was not mirror maker solution, right? This was just the source cluster.
Question.
Sure.
When you say put reducers, that's from the output of the Venus box.
That's right. On the leftmost box.
Right.
Here.
So you have less links going into the Kafka mirror.
That's right. Yeah. Well, no. If you remember, there was Hadoop cluster here, a yellow one. Data going from that to the Kafka cluster. There were like 800 producers.
Oh, that's the one you reduced.
Yeah, that's the one we reduced.
Of course, the output of Venus is also reduced.
Well, amount of data is still the same. It's just that how many active producers there are, we change that, reduce that. In mirror maker specifically, we increased number of cores. So we had eight consumers and one producer, right? So we changed from 4 cores to 8 cores so that all consumers can go parallel with real concurrency. I think we did not increase partitions, but because of reasons here, having 200 partitions and 80 consumers doesn't give you a good kind of balance because only two or three partitions per consumer is kind of on the low side. But I think I will leave it at that. What we really changed was producer batch size. So this was limited to about 100K when we ran the experiment. We increased up to 1 megabyte. And because of that, now producer that is going over long distance link can batch significantly more. Remember, we did not move the cluster on the other side. We just increased the batch size. And we also increased the buffer sizes to 10 megabytes. And that really did the trick, except there was a bug. That in cases when, in some cases, not in all all push really, in all applications case, only once in a while the data used to be larger than 1 megabyte. The producer used to miscalculate these, misestimate the size of the batch, used to send out something which is larger than 1 megabyte, and our brokers were configured to say, hey, nothing more than 1 megabyte is allowed. So it used to send back not request too large, and mirror makers used to simply die. So we ended up disabling compression estimation. I don't have to go into details of that, but this is what kind of tends to happen. Like when you're at the edge of the system, you hit a bug at the kind of worst time. So what we ended up doing was, we didn't disable compression. We disabled compression estimation. So what it used to do to fix it, get data, fill up a 1 megabyte batch, compress it to up to 650K on average, and send it out. The earlier code used to okay, I have 650, maybe I can pack a little more, and it's used to go up to 900, and it's used to crap out at some time. So we simply disabled compression estimation. That left us almost 30% unused capacity, right? We could go up to 1 megabyte. So that was clearly an indication that, look, we can go even higher batching if we fix the bug. But this was actually good enough, because as soon as we did this is what we got. All the pipelines finished integration in under about 23 minutes, and our SLA was about 30 minutes. And this is how a truly global, well-behaved pipeline might look like, a single topic being replicated.
Did you apply the fix to all regions?
That was not necessary.
Or just Asia and...
That's right, Asia and to West Coast.
Have you applied it to the East Coast and Gulf Coast? Would you see improvement as well?
Potentially.
I know you missed your SLM, just short.
Yeah, well, maybe not, because in case of East Coast, they were the mirror makers, and both clusters are on the same data center, so it's pretty fast. And in case of Gulf Coast, we had the mirror maker was on the other side. It was doing remote consume. So the improvements were all specific to producers. So
the CPU was already high, right, for the East Coast?
yeah,
The CPU was already high, so they probably don't have capacity.
that's right. That's right. It was pretty much pegged at 100% in both cases. Yeah, the good cases.
Where was the bug again that you isolated?
Yeah, so the bug was, it's been fixed now. It's basically, it used to miscalculate.
No, which box was it on there?
Oh.
On the pipeline?
Which box? I thought which bug.
No.
It's okay, I'll go back to
The
the
whole pipeline, where was the
picture.
bug on the picture?
Sorry, is this the right diagram?
I don't know. Where's the bug there? Where was the bug?
Oh, the bug was over here.
Oh, okay. The
Well,
mirror
I should
maker.
go back to the before the animation. So we didn't move them. The producers over here were batching poorly.
Oh, so
Okay.
mirror maker producers.
Yeah, mirror maker producers were batching poorly. So we improved. We fixed the bug here and got more batching.
So it's a workaround, right?
It was pretty much a workaround to save the week.
Right. Until the next release.
That's right. That's right.
And then
Yeah, so that is pretty much it. The CPU performance of all mirror makers after the fix look kind of like this. It was hard to beat, such a smooth, ideal chart like that. But they were kind of okay, pretty high, maybe 60-80%. We got our SLA, so we were happy with it.
so lesson learned, pay attention to your buffer utilization.
That's right. Yeah. Paying attention to all these metrics is like the most important thing that you can do when you're running Kafka pipelines.
Yeah. It's like maintaining a jet engine to fly across it.
Okay.
That's what pilots do. They maintain ratios. They don't maintain RPMs like you do in a car.
Right.
They maintain ratios, which means buffering of airflow through the engine.
Interesting. Yeah. It's complex engineering systems, I guess.
Why is the max buffer size capped at 1 megabit?
We just had that. I think it could go higher, but our brokers were configured to have no more than that. It's just that extremely large request. This is just one partition, right? You could have, I don't know, 50 partitions. So your request is 50 megabytes large. That kind of creates memory pressure as well if you go even higher. So there's, I think, a limit to that, how large it is.
Is it configurable, or was that a hard upper bound?
No, it's not a hard upper bound. It's configured. So that's pretty much it. This presentation and all this experiment wouldn't have been possible without Kafka team support as well as Venice team. And if you want to read about Kafka and Venice, there are articles. You can just Google them, of course. I have a link here. And that's it. Any other questions? Thank you for attending.
Yes. So,
one message result, one megabyte.
I see.
So I just simply send this message.
Probably because, yeah, 1 MB is pretty good and pretty large. I mean,